So Carlos volunteered to do all of today's problems.
No problem, I think I have.
Feels bad for missing yesterday.
I was in the Zoom though.
I did see that, but you weren't here in person.
Yeah.
Right. Happy Friday. We're going to finish up with double integration today. We're going to look at integrating in polar. But remember polar coordinates. Right, they're of the form r theta. R is the distance from the origin to the point. And theta is the angle that the segment OP makes with the positive x-axis. So this means that polar regions, generally speaking, are circular. So if we have a domain that is circular, probably advantageous to just go ahead and do it in polar coordinates. As was the case with the last problem we looked at yesterday, right? Our region of integration is a circle, which means this is much easier to integrate in polar. Right, so remember we originally defined D in rectangular as the set of ordered pairs xy such that x is between -4 and +4. and y is between negative square root 16 minus x squared and positive square root of 16 minus x squared. We now want to describe that as a polar region. Well, it's a circle of radius 4, isn't it? It's going to go less than or equal to. Bless you. So our volume now becomes integral 0 to 2 pi, integral 0 to 4. We now need to convert the integrand, 16 minus x squared minus y squared, into a polar function. A polar integrand. Well, that should be easy to do, right? What is it? You just told me it was easy.
Um, 16 minus r squared, cosine squared theta.
You're doing too much. X squared plus y squared is r squared, right? Which you would get by replacing x with r cosine theta, y with r sine theta, and then simplifying. Just 16 minus r squared. Now, here's where things change just a tiny bit. dA is not dr d theta. It is r dr d theta. The most common mistake, bless you, when converting to polar, the students forget that extra r. Is there a theta anywhere in the integrand? Do the bounds for r depend on theta? Fubini's theorem says order in which we integrate does not matter, so why not integrate with respect to theta first? That's just the length of 0 to 2 pi, which is 2 pi. Two pi times the integral 0 to 4 of 16r minus r cubed. You know, 8r squared from 0 to 4, which is 8 times 16, minus a quarter r to the 4th from 0 to 4. No, that's 4 cubed. 256. It's 4 to the 4th, which is a quarter of 256. All right, 8 times 16, that's 2 to the 7th power, which is 128. Volume's 128 pi. Assuming I did my arithmetic correctly. Which is what you should have gotten when you did it using rectangular. With a lot more algebra. Gonna go ahead and integrate x squared plus y squared raised to the 3/2 power over the disk x squared plus y squared less than or equal to 36. Let's see. Right. So notice something. The integrand x squared plus y squared all raised to the 3/2 power. If we were to try to do this in rectangular coordinates, you couldn't. You have to convert this.
You determine if you solve it or not. Or you just try if you can.
So if we try to do dy dx, what function has a partial derivative with respect to y of x squared plus y squared to the 3/2? There's none. Same thing with x. If you try to do it with x, you can't find an analytic anti-partial. So it cannot be done with dy dx or dx dy. So you have to convert. You don't have to convert to polar. Right? You can also use what's known as a Jacobian to convert to any arbitrary coordinate system. Sadly, we don't have time to cover Jacobians. If you're interested, there is a section in your textbook on it. Read through it. It is essentially the U sub for multiple integration. It's the change of variable for multiple integration. Which is, by the way, what converting to polar is, right? It's a change of variable. But using a Jacobian here wouldn't make sense because x squared plus y squared less than or equal to 36 is a polar region. Right, this would be way easier in polar. So what we want to do is describe the region in polar coordinates. So it's a set of ordered pair r theta. What are the bounds for r? What about theta? The entire circle, so 0 to 2 pi. What does the integrand become? Check again. It's r cubed. It'd be r squared to the 3/2. And then the differential. R dr d theta. By convention, we always write it as dr d theta and not d theta dr. So by convention, your bounds of r are always going to be functions of theta. And then your theta is always going to be constants. It's not a rule that's set in stone. You could write theta as a function of r and then do r as constants. Right, and then do d theta dr. There's no theta in the integrand. R does not depend on theta. So the integral from 0 to 2 pi of d theta is just 2 pi. Fubini's theorem. You can flip the order of integration. Because r doesn't depend on theta, you can literally just flip the bounds as well. Right? You don't have to redescribe the region because neither of those depend on, right? They're not functions, essentially. The bounds are constants. So that would just become what? Integral 0 to 6, integral 0 to 2 pi of r to the 4th d theta dr. And then that's just the integral with respect to r times the integral with respect to theta. Oh boy. 5th r to the 5th from 0 to 6 is going to be a 5th times 6 to the 5th power. What is 6 to the 5th? What was it? Oh, it's unacceptable. Should have been all 7s. That would have been cool. Two times 7776. $15,552. So 15,552 pi over 5 is our integral. So we're the disk x squared plus y squared less than or equal to 36, right? So since r is the distance from the origin to any point in the region, obviously 0 is the smallest r can ever be, right? That'd be if you're at the origin. Well, how does the radius change over that disk? Remember, you're inside the disk. Goes from 0 out to the radius, right? Which is 6. Right, because it was the entire circle. It was 0 to 2 pi. Find the area of the region that lies in the first quadrant between x squared plus y squared equals 36 and x squared minus 6x plus y squared equal to 0. And then it was x squared minus 6x plus y squared, right? Yes. We're in the first quadrant, so we're going to plot the first quadrant. 0 to just going to go to 10. Turn off the frame. On the axes. Just to be safe, I'm going to specify I want the origin to actually be the origin. Let's find some interesting colors. Saw a bird up there. I want that bird. Come back. Let's make one of them dark yellow. Why not? And see, I don't need to do anything. Bless you. Okay. These have been the latest colors for like a week. Let's look at the trending colors. Vivid purple. Oh, it's a butterfly, even better. Does not look like dark yellow on that screen, but we'll make do. Right, and then the region we're interested in. Be right in there, wouldn't it? Let's make that maybe a tad bit smaller. There we go. Well, this just looks like a bloody nightmare to do rectangularly. So let's try it in polar. So bounds for R. I agree with 6 being the upper bound. Which is what? Needs to be written as a polar. So what's R? Y negative 6 cosine. Right, but you're solving for R, right? So it should be positive 6 cosine theta. Which it is. Right, the smallest value R can possibly take on in that region is 6 cosine of theta. Which does give you 0 as an option. Right, but R has to lie somewhere on this purple line at the smallest, right? Because we're in between. Now, what about theta? Y pi. All right, so Y pi. For instance, 2 pi over 3 is between 0 and pi, right? Is that quadrant 1? Go up to pi over 2. 0 to pi would be the first 2 quadrants. So there's the description of our region. Remember, area of the region is just the double integral of the region, or double integral over the region of just the area differential. So the integral 0 to pi over 2, integral 6 cosine theta to 6, r dr d theta. Sadly, r depends on theta. So we can't just integrate with respect to theta first and say it's pi over 2. Gonna have a half r squared evaluated from 6 cosine theta to 6, which is 36 minus 36 cosine squared. Pull out the 36 over 2. Integrand becomes 1 minus cosine squared. There are 2 ways to proceed. They would both give you the same integrand. Could rewrite 1 minus cosine squared as sine squared. And then use the reduction identity on sine squared to get 1/2 minus 1/2 cosine of 2 theta. Or you can just use the reduction identity on cosine to write cosine squared as a half plus a half cosine of 2 theta, which when you simplify gives you 1/2 minus 1/2 cosine of 2 theta. Then factor out that 1/2. You have 9 times the integral of 1 minus cosine 2 theta d theta. What is the period of cosine of 2 theta? What's the period of cosine? Is that for cosine or cosine of 2 theta?
Cosine. It would be pi. No.
Cosine's period is not pi. Tangent's period is pi. Uh-oh. Period of cosine is 2 pi. So then what's the period of cosine of 2 theta?
Pi.
Would be just pi. Bummer. We're not integrating over a full period. That means we actually have to integrate cosine of 2 theta. That's a bummer. So our antiderivative cosine 2 theta would be a half sine of 2 theta. Sine of 2 theta evaluated from 0 to pi over 2. Going to be sine of pi, which is 0, minus sine of 0, which is 0. That winds up giving us 0 anyway. Our area is 9 pi over 2. Which, if you were masochistic enough to try and do this in rectangular coordinates, you would get 9 pi over 2, which means you're going to wind up having to do trig sub. Gonna graph r equals 1 over 4 cosine theta and r equals 1 between negative pi over 2 and pi over 2. Then we'll go ahead and find the area inside the curve r equals 1, but to the right of 1 over 4 cosine theta. Fucking me. There you are. And use the polar plot command. This allows us to plot functions of the form r equals f of theta. Well, we have two of them, right? We have I don't feel like going through the command to get theta, so I'm just going to write out theta. 1 over 4 cosine theta is the same as a quarter of secant theta, right? And then we also have r equals 1. We're told we only want this plot for theta between negative pi over 2 and pi over 2. Yeah, plot style. That should be all I need. It is. Okay. Almost. Notice what polar plot does is it plots it on the XY coordinate system. There is an option to turn off the XY axes and turn on the R theta axes, but they're not really useful if you've ever seen the R and theta axes. They're not useful. R axes are just rays, and then the theta axes are the circles. So we're going to leave it on the XY. That means that those ticks are useless. I'm gonna turn them off. Perfect. All right, so this is r equals 1. Secant of theta over 4 is just this straight vertical line. Our region was inside r equals 1, but to the right of a quarter of secant of theta. Oh dear. How big am I going to want that? Oh. That should be good. So that there would be the region that we're trying to find the area of, right? Oh, for Pete's sake. Why are you doing this? Fine. 2 can play this game. Really? Oh dear. What's going on? Victory is mine.
Didn't focus.
My computer would probably be back there. So I have insurance on it, so. What happened? Oh, there was a hole in my bag. It fell out of my bag. And I was upstairs and it tumbled all the way down the stairs. So we need to describe this region in polar. What are the bounds for R? And this should actually be simple. Slightest bit? That was the slightest bit. So what are the bounds for R? And again, it's actually simple. Don't overthink it. Not 0 to 1. It's a quarter secant theta to 1. Right? What's the smallest distance from the origin? That line, right? Which is a quarter secant theta. Largest distance it can be is the circle. And it was simple because it was already given to us in polar. So we didn't have to worry about converting it. That's nice. Now for theta. What are the bounds for theta? It's not that simple. Right? Negative pi over 2 to pi over 2 would be, you can do that entire thing, which we're not, right? We're rotating. Here. Find those angles. Which is not difficult to do. Just set the r's equal to each other and solve for theta. Right, they're the points of intersection. Secant theta would equal 4. So the angles would be plus and minus the inverse secant of 4. Or, if you prefer, plus or minus the inverse cosine of a quarter. Right, obviously the positive is the one up there, the negative is the one that's down below. I actually want to do. I do. Yeah, I'm going to want to use cosine. Does everyone see how I got the angles? Perfect. I'm going to make a substitution because I don't feel like writing inverse cosine of a quarter. So I'm just going to replace it with psi. This is a very common practice in mathematics and physics. If you have a constant that's tough to write out and you're going to be writing it a lot, just replace it with some letter or some symbol. Right. For instance, one of the most common ones in quantum mechanics is h bar. think it's the reduced Planck length. We're again looking for area. So it's the double integral over the region of the area differential. And then dA becomes R dr d theta. R squared over 2, I'm just going to factor out that 1/2. So R squared from 1 to a quarter secant theta. And we get 1 minus a 16th secant squared theta. Length of that interval, 2 times psi. Antiderivative of secant squared. It's just tangent. And of course, that's going to be evaluated from negative psi to positive psi. So we get tangent of psi minus tangent of negative psi. Distribute that half through. Actually, it's just that, and who can tell me why? Your trig instructors would be very sad right now. Why? That's not why. You're not allowed to factor out of a tangent because it's a function. What is that property known as? Tangent is an odd function. Definition of an odd function, f of negative x is equal to negative f of x. So tangent of negative psi is the same as negative tangent psi. So that difference is 2 times tangent of psi. Excuse me, 2 times tangent of psi. Now we just have to replace psi with what we said it was. But that answer is unacceptable. You can simplify tangent of the inverse cosine. Say that angle there is psi, which is of course the inverse cosine of a quarter. That means cosine of that angle would be 1/4. Cosine is adjacent over hypotenuse. Means that missing length is √15. Tangent is opposite over adjacent. So the tangent of the inverse cosine of a quarter is square root of 15. And there's our area. I think I'm going to skip for and do this one. We want to convert this integral. Oh, if I actually completed the sentence. To polar coordinates, and then we'll evaluate it. Going to make use of the region plot command. So our region, which you can read right from the integral, negative square root 9 minus y squared has to be less than or equal to x, which is less than or equal to 0. And then negative 3 is less than or equal to y, less than or equal to 0. To gray. I wonder if all those errors because of how I set up -5 to 5, probably. So I can just ignore those errors. They're not important. What is important is there's our region. Gotta be kidding me. Huh? Okay, so where did it go? Saved it in the fucking OneDrive. Desktop, yeah. Oh, it didn't save it as a bloody JPEG. Write that as a polar region. R goes 0 to 3, doesn't it? What about theta? Right now I have to rewrite the integrand. R sine theta over r squared plus 1 times r dr d theta. For the sake of time, that winds up being inverse tangent of 3 minus 3. It's actually not too difficult to do. Just have to do method of partial fractions, and then actually you don't even need to do partial fractions, just do polynomial long division. To rewrite r squared over r squared plus 1 as I think it's 1 plus 1 over r squared plus 1. Questions on polar coordinates? When converting your differential, do not forget that extra r that appears. Means next week we start triple integration.